We can hear you. We can hear you fine.
Okay, good. Then let's go ahead.
So good morning again, and let me introduce Gerhard Knieper, who will give the second class of his course on coarse hyperbolicity, measures of maximal entropy, and growth rate of closed geodesics.
Okay, thank you very much. Welcome to my second lecture. So first let me recall what we did last time. So what we studied were Riemannian manifolds without conjugate points. I explained what that means. That means especially that, or implies, I should say, that the universal covering is diffeomorphic to Rn, that's denoted by X, and gamma is the group of deck transformation acting on this space. And then we put some hyperbolicity conditions to this structure, namely, which are denoted by H1 and H2. And H1 is simply the existence of a background metric of negative curvature. So I assume that my manifold carries a second metric, which has negative curvature. And H2 is a kind of divergence property, which means that if you take geodesics a geodesic ray starting at the initial point, at the same initial point on this universal covering, which I equipped with a lifted metric, then the two geodesics diverge. So this, of course, if you are non-positive curvature, which implies no conjugate points, then this is automatically satisfied. And but in general, it's not known if this condition H2 is actually satisfied. Okay, now today I want to introduce a useful and very well studied measure on the bound. So I should also recall that I introduced a boundary structure to the universal covering, which is called the ideal boundary, which lets me compactify this the full universal covering. And what we do today is to introduce a very well and useful measure on the boundary, which is called Paterson-Salville measure. Actually, it's a full measure class. It depends on some chosen point. And when you define this measure, you usually start off with a certain series, which is called the Poincaré series. So what does it mean? You choose any 2 points on the universal covering, and you choose a real parameter S, and then you look at this exponential sum. So you sum over all elements in the group, in the deck transformation group gamma, and you sum exponentials e to the minus s d, the distance of b to gamma q. So if gamma q moves and the orbit somehow will be distributed on the full universal cover, and that's what this series actually measures. Okay, now this is just a formal sum. And the sum, what I want to show first is that the sum converges if S is independent of P and Q, if S is larger than H, and diverges if S is smaller or equal than H, and H is a number which I also introduced last time. It's the topological entropy of the geodesic.
So D is just the lift of the Riemannian metric?
D is a lift, everything is lifted onto X.
Okay, thank you.
So the metric, when I talk about geodesics on the universal covering, I mean always geodesics with respect to the lifted metric. Okay, and then the series converges for S bigger than H, what I already said, and for S smaller or equal than H, it diverges. And H is a topological entropy, and by this result of Very and Manier, which I mentioned last time, this can be expressed geometrically by an asymptotic quantity, which is given by the logarithm of the volume of geodesic spheres. Last time I said balls, but works also for geodesic spheres, divided by R. So geodesic sphere is simply the points on the universal covering which have equal distance from R from this point P. Okay, so that's what I want to show. And when you prove this, it's the most easiest proof is to choose a fundamental domain of this gamma action. And the fundamental domain is, of course, compact, because the manifold was right from the beginning a closed Riemannian manifold. And now you average the sum with respect to the Riemannian volume. And since gamma acts isometrically on the universal covering as stack transformations, you can somehow replace this integral by an integral over the translated fundamental domains, and the gamma disappears, and instead of gamma you have here, you replace, oh I said here gamma, yeah, you replace f by gamma f, and that is of course the same as integrating over the full universal covering, and what remains to be integrated is just this exponential function. Okay, now it's natural to introduce polar coordinates, which you can do the same manner as in the Euclidean space. So you take polar coordinates around this point P, and this integral over x can be written as an integral from 0 to infinity, e to the minus sr. R is just the distance from P to Q, times the volume of the geodesic sphere. So, and then it's, you ask yourself, when does this integral converge? And clearly by the notion of, by the way of writing the topological entropy, you see that it certainly converges if S is bigger than the topological entropy, and it diverges if S is smaller than the topological entropy. And the question is, of course, what happens at this critical point when S is equal to H. And so this is a bit more complicated to prove, but a slightly different modified argument then yields also divergence for S equal to H. So of course, this full theory, what I'm explaining here, is done in a much more general context. You can do it with metric spaces, Gromov hyperbolic spaces, and so on. And then it's often not so clear, especially if the action of the group is not a co-compact action, whether you have convergence or not, divergence or not. So here in this case, you get divergence. Okay, so then you have this property of the Poincaré series. You know exactly when it converges and then diverges. And now I want to introduce this measure. So where I'm here, yeah.
Sorry, before you go, did you explain to us that H is finite or not? This entropy?
Because first of all, we are on a compact space.
Mm-hmm.
The topological entropy of a flow on a compact space is a differential is somehow bounded. Time one map saying is clearly that this is bounded, but another argument is given by this formula of the topological entropy, because volume can only grow exponentially and not faster than exponential. So this is certainly a finite quantity. Of course, if you are in a non-compact setting and assume that you have no bounds on curvature whatsoever, then of course it could be different. But here in this case, it's certainly everything is finite. Okay, now I come to this very nice measure, which was introduced by Paterson in the case of Fuchsian groups, and then was very much studied by Sullivan, and then it was used in a more dynamical way, and I used it also in non-positive curvature and so on. And but the construction of the measure is basically always the same. So what does a measure? What's the information of this measure? So you start with a point on the universal covering, and you are interested in the orbit of the Deck transformation group, gamma x. So you want to measure how this orbit is distributed in the universal covering. So now at the beginning, you start with a parameter which we had before, which is larger than the topological entropy to get something finite. So you look at a measure which is formed by Dirac masses on the orbit points, but they are weighted with an exponential term. And the exponential term gets smaller if the orbit moves to infinity. So it gets exponentially small, and you sum over all groups of the Deck of the Deck transformation of all elements of the group of Deck transformations, and then you normalize it by the Poincaré series Ps x, x. This is important to have this normalization, as we will see. So as I said, you can think of this measure as the distribution of the lattice, or the orbit of the lattice with respect to this fixed point x, seen from observation point. So P is a fixed point, and now you want to measure how the distribution of the orbit looks like seen from this point P. The first thing which you somehow realize is that the measure is actually bounded. So that's a simple consequence of the triangle inequality and the fact that the gamma acts isometrically. So if you look at the full measure of the full space x, or even x bar, the compactification of this space x, then you see that's bounded uniformly from above and below by e to the s distance from p to x, and from below by e to the minus distance from p, x. So this is a family of finite measures, and now that's not what you are interested in. You are interested in how the distribution somehow behaves at infinity.
Hi, Gerhard.
Yeah.
I think there are some Dirac masses missing on the numerator, right?
Something missing here?
The Dirac masses?
No. I'm taking, I'm sorry. I take here the measure of the full space. That
okay. I see.
Each point has mass 1.
Okay, great, thanks.
What I'm saying here is that I want to compute the total measure of this, the total mass of this measure. So that means I take principle, what's written here is mu p s x applied to the full space x, or x bar. X bar will be important because I go to the limit later on when s tends to h. But before that, it's simply a finite measure which is bounded away from 0. Okay, that's this calculation. It's simply triangle inequality and the fact that gamma acts isometrically. And right from the beginning, it's clear that the support of the measure is contains the orbit gamma x, and is contained in the closure of gamma x. So that's more or less by definition. And now comes the interesting point. You take a weak limit. So now it's important that I compactify everything, because otherwise it's not so clear how to take a weak limit. So you take a weak limit for a certain for some sequence which approaches h from above. So you take this sk, you choose such a parameters which converge from above to h, and then you choose such a big limit. And now it's important that the normalization becomes important, because the series in the denominator here psx converges to infinity. So the orbit does not, the orbit, if gamma x is in a finite region, it's not going to infinity. The mass goes to 0 for all points gamma x which are not moving to infinity. In other words, what I want to say is that the support of the limit measure will be not on the orbit, only on the closure minus the orbit. So the support of the measure moves to infinity, so to speak. And this is usually called the limit set of this orbit. So it moves into the limit set of the orbit. Okay, now you can show that if you have such a weak limit for P, you also have the same weak limit for Q. So it doesn't matter which point you choose, you get the same, you can choose the same weak limit. And in this way, I get measures which depend on the observation point P. So I get a full family of measures. For each P, I get a measure. And now it becomes important what kind of properties this measure have. The first property is more or less obvious. Just as a consequence of the fact that gamma acts isometrically on the full space X. So if you have any Borel set, so we have a topology on this boundary, then you have that for all elements gamma, if you move the set by gamma and you move your observation point P to gamma P, then you didn't change anything. So you get the same measure. So this is this kind of gamma equivariance. And the second point is maybe a bit less obvious. If you move the measure from P to Q and take the radionegative derivative, you can show that this exists and is exactly given by e to the minus h times the Busemann function based at this point at infinity psi of q comma p. I will come to that how one can see this.
Sorry, the limit measure also depends on the sequence sk in general?
A priori, it depends on the sequence.
Okay.
A priori, it depends, everything depends on everything. Later on, I won't do that, but you can prove that it's independent of the sequence. And actually, one can even prove that the three properties which I've written down here uniquely determines the measure up to a normalization. It's not, but that's a different story. And the last property is the support of all the measures mu p, one and therefore for all, is a full boundary in this case. A priori, it would be maybe only the limit set, but in this case, which I'm studying here, it's a full boundary. Okay, let me quickly go through these assertions and try to convince you that this is reasonable. Point A is basically follows from the definition. There's nothing special going on here. As I said, it uses that gamma acts isometrically, and the definition of the measure. Okay, the second point is with this radionegative derivative is let's look at this picture at the beginning. So if x is very close to, say, a point psi, then you compare. You only have to sum over orbit over the orbit parts which are very close to this point psi, and this means that you somehow want to replace differences of distance function, namely the difference of q to gamma x and of p to gamma x, if gamma x is very close to this point at infinity. And if you remember the definition of the Boseman function, that's precisely if gamma x converges to psi, this will be exactly the Boseman function based at psi with respect to q, p. The Boseman function somehow is a signed distance and measures how far, in some sense, the point is away from infinity. Or better, it measures these differences, and therefore you can replace this the differences of the two distance function by the Boseman function. And if you look at the definition of the Paterson-Sullivan measure, it somehow involves this distance function. You see that the denominator will somehow disappear because you take quotients, and the denominator does not depend on the point p. So it only depends on x. Okay, so that's basically in a nutshell the proof of part B. And part C is basically a consequence of A, the gamma equivariance, and more importantly, it uses the fact that gamma acts minimally on the boundary. So how do you see this? Either you use the fact, you probably have to use the fact that you have a background structure of negative curvature, and the hyperbolicity of this negative curvature, you can also, the hyperbolicity you can see also on the boundary. So the action of gamma with respect to at the boundary, with respect to the negatively curved metric, and the metric which we have chosen is not really different. So because you have an isomorphism between the two boundaries given by the negatively curved metric and given by the metric without conjugate points, and then you use the fact that in negative curvature the gamma acts minimally on the boundary. So this is really uses somehow that you have this background metric of negative curvature. So that are the three important properties. So I won't prove that these three properties will determine the measure uniquely, but you can do that. But I will not use it in my lecture. Okay, one remark, interesting remark, is that this measure somehow is in some sense quite uniform. So if you pick a horosphere, say based at psi, which passes through this point P, and you take a geodesic coming from this point psi, then it of course will intersect the horospheres perpendicularly. And if you move now the measure from, say, P to CT, then the measure will change by the rate e to the minus ht. So in other words, if you move from one horosphere to the other horosphere, then the change of the measure will be uniform by the distance e to the minus h distance of the two horospheres. So in other words, if you are further away from this point and infinity and further away with respect to this horosphere, so if you have distance t from the horosphere through p, then it's e to the minus ht if you are outside the horosphere and e to the ht if you are inside the horosphere. So it's like, it reminds you if you are familiar with Margulis measure, the Margulis measure is doing more or less the same thing. So it's a very uniform behavior in radial geodesics. So also another word you can also think of stable manifolds. So if you would now somehow push the measure on the stable manifold, it would have this uniform scaling. So that's what is somehow, of course, one of the main features of the Margulis measure. Okay, that's what comes out from this construction. And now Sullivan, he actually proved a very important second property of the measure, which is the so-called shattering lemma. So shattering lemma we will use a bit later, especially if we want to introduce an invariant measure for the geodesic flow based on this Paterson-Sullivan construction. The shattering lemma will be very important. So what the version which I'm looking at is the following. So you fix a point at infinity, and you look at the projection from this point at infinity. So you project your full space again to the boundary by taking a point psi. So you fix a point psi, and you take a geodesic joining psi and x. So in the sense that the geodesic is at infinity is initiated from psi and passes through x. And then the image of this projection is then the opposite point. So this one, yeah. This, of course, defines your map from x to the boundary depending on this point psi at infinity. So it's this kind of radial. So you can draw here radial projection. Okay, so that's the map, which will be important for telling you what the shattering lemma is doing. And now comes the quantified shattering lemma, which tells you the following. There exists a constant which depends on the metric without conjugate point and the background metric G0, which is a metric of negative curvature. So I cannot say anything about this constant, but it's a universal constant. And a second constant b bigger than 1, such that if you look at any geodesic connecting p to x, and you look at the initial point of the geodesic at infinity, so you go backwards on this geodesic to infinity, then you can do the following. You can project a ball of radius rho. Rho is precisely the constant which I mentioned here at the beginning. It can be also larger, but not smaller. You project this ball to infinity, and the projection is done with this map which I introduced, seen from this point psi. So you take the point psi and you project the ball to infinity, and then you get some z. Okay, and if you choose this ball sufficiently big, then you have the following estimate. So the estimate of the measure. So you choose P is a point on the geodesic between psi and psi, x. And if you move now your point P on this geodesic further away from this point x, the measure becomes smaller and smaller and smaller in a uniform way. So it's basically proportional to e to the minus h, the distance of p to this point x, which is the center of the ball which you project. So it decays, if the point p of the measures will move towards psi, it becomes exponentially small. And this is more or less clear. So if you move the measure further away, somehow the measure of this projected ball gets smaller and smaller. Okay, this is what is called a shattering lemma, and this is not dependent on what point X you choose. You can take any point X. The only important thing is that the point P moves on this geodesic joining psi and X. So this is a shattering lemma. And let me quickly tell you why this is true and why this constant rho appears. The first remark is, if you are in the setting of negative curvature, you can take this constant rho as small as you wish. So you have to fix it, but you can take it 1 or whatsoever. In our setting, this is not possible, and in principle, it could be if the ball, the radius of the ball is too small, and you project this ball to infinity, you see only 1 point, because you have geodesics which stay in a small tubular neighborhood, and of course, the tubular neighborhood cannot be too large, because this is this Morse shattering, which I explained last time. But in principle, if rho is somehow too small, the projection could principle be just 1 point and infinity. Think of this situation that you have this kind of behavior. So we have this all geodesics going through this ball will somehow stay in bounded distance. So that can happen in our situation, and therefore we need this constant. So more precisely, the Morse shattering guarantees the existence of a constant rho depending on these two metrics, such that this projection, maybe it's not open, but contains an open set. So that's the first fact. So you need that this projection here of the set, that this contains some open set. And now you use the fact that the support of the measure has full support, so it's positive on open sets. And this implies that at least for a fundamental domain, for some compact region, the measure of the set, of this projected set, is larger than a certain constant. Okay, that you would get first only for a compact set. And then you use the gamma equivariance to get this actually for all x. So it's gamma equivariance somehow yields that this estimate, which I have here, the green star, holds for all x and all psi, x in the manifold and all psi on the boundary of the manifold. So you have this uniform constant. So that's the first thing, that is in this sense, it's bounded from below. And then the second thing is, if you move this point X to another point P along this geodesic, which I mentioned, then the following happens. So you use the fact that all the measures mu P are absolutely continuous, and you can replace this integral here, this measure here, by an integral of the projection, and you integrate the Radon-Nikodym derivative of P to X, and you integrate over all the points on the boundary which are in the shadow of this ball seen from this point psi. So this is just another way of writing, applying this Radon-Nikodym derivative. Okay, so you have this Busemann function here. And now you want to replace the Busemann function somehow by a distance function. And if you think of the set which you obtain as a projection, then it looks more or less like in this picture here. So if you take at eta eta, you have to integrate over all etas, but if you take eta, basically the center of the ball, which is a projection from x somehow to infinity, then the Boseman function will be exactly the distance from p to x, from here to here. Now but you are not at this point, at the center for eta, maybe here, point nearby. And then you have somehow to replace it. You can also replace it by the Boseman function, by the distance function, but only up to a certain constant. So that's basically here. So you can, if you have eta here instead of this point, then it's not quite the distance function, but it's a distance function up to a constant. And if you plug that estimate into the integral, you get basically the shattering lemma to get this estimate. So whatever.
I'm sorry. In this last step, you use just continuity of Boseman function.
I use some continuity. Yes.
Just continuity. Yeah.
I use continuity.
Yeah.
Otherwise, it would not work. So I use continuity.
So I also have a question. So your hypothesis include the non-positive curvature case?
Yeah, you have to be in principle, yes, but not quite, because you know, I mean, if you study a little bit non-positive curvature, there are some strange non-positively curved manifolds, not strange, but which do not admit any negatively curved metric. There's this Gromov example, which yields a non-positively curved rank 1 manifold, which has a property that Z2 injects into the fundamental group. So you have some torus, yeah, and this is torus somehow is a submanifold of this 3 manifold, and this will yield somehow a subgroup of the fundamental group, which should not be there if you are in negatively curved space. So in negative curvature, the only a billion subgroups are the group Z, so there's no other group. So that means that it's not quite non-positively curved. But the same proof which I'm giving here would also work in a non-positively curved setting. So this is, and it works in Gromov hyperbolic spaces and so on. So it works in a general context of situations. Okay, so that's this famous Paterson-Salvin measure. So now that's what we actually are using later on is this shattering lemma and the properties of the Paterson-Salvin measure. But we are not interested. We are interested in dynamics, so we are interested in the dynamics of the geodesic flow, and therefore somehow the issue is to construct now an invariant measure for the geodesic flow, which is based on this Paterson-Salvin measure. So the naive thing would be somehow the geodesics you can identify with geodesics on the universal covering, and each geodesic will give rise to 2 points at infinity. So it would be natural to take a product measure or on the boundary, but if you do that, you take the product of 2 Paterson-Salvin measures. It will work. It will give you an invariant measure for the geodesic flow. Unfortunately, it will be not gamma equivariant. So it will not. You want to have a measure which is defined upstairs, but should somehow descend to a measure on the quotient, on the unit tangent bundle of the quotient. And for doing this, you need what was already introduced yesterday in another talk, the so-called Gromov product. So I have to explain what the Gromov product is, and then I will do what I just mentioned to take a modified almost product structure on the boundary, a product metric on the boundary. Okay, so let me recall, so I still have the same assumption, which I mentioned here. So Riemann manifold without conjugate points and these conditions, H1 and H2. And I have to explain what the Gromov product in our setting is. So the Gromov product depends on points in infinity and choose the reference point on the universal covering. So what are you doing with this? So you take 2 points at infinity, psi and eta, and I draw 2 Horo spheres which are passing through this point P. Then they will intersect, of course, by definition, and I can think of the interior of the Horo spheres, which are usually called Horo balls. So this kind of things here, the Horo balls. And the 2 Horo balls will cut out a piece of the geodesic joining psi and eta. And the Gromov product is precisely the length of this piece. So you look at this red piece. So let's see, maybe this here will be the Gromov product, and it's usually denoted by BP psi eta. So that's basically the geometric explanation. But if you want to have a formula for that, you do it slightly differently. So you know that the levels of the Boseman functions are the Horo spheres. And what you do is you choose a point Q, any point Q on this geodesic. So let's say you have here some point, sorry, Q on this geodesic. Which one you choose doesn't matter. And now you take the Boseman functions of one Boseman function is based on at psi, and the other Boseman function is based at eta. So this is here. And you normalize it by this point P. That means that the 0 level of the Boseman function is a Horo sphere passing through P. So you have that the 0 level of these 2 Boseman functions of psi, with respect to psi and eta, up the 0 level is exactly the Horo sphere passing to P. The 2 Horo spheres passing to P. And now you have to remember what I said last time. Another way of interpreting the Boseman function is that it gives somehow the distance of a point to, so this Boseman function B psi P is nothing else than the signed distance of the point Q from the Horo sphere through P. Now you have two, so if you have now point Q, you have maybe if it's inside, you have here minus and a distance from the Horo sphere to P, from the Horo sphere to, with respect to eta, through P, and you subtract, you add, okay, maybe it's more or less clear. So if I choose this point Q, what is the first expression here? B, C, Q, comma P will be, that will be in this case, minus the distance of Q to HP. That is because Q is inside, oh, I'm sorry, it's, I think it's the opposite way around. Here, this is equal to minus the distance of Q to HP. And here Q is outside the Horo sphere through P seen from psi. So this is HP, so it's eta. And this is a distance plus the distance of Q HP eta. And what's remaining is actually really the distance, is the length of this geodesic, which is cut out by the 2 Horo balls. So maybe I did not explain it well, but that's what's coming out.
I guess that the first one is HP zeta, right?
Yeah, exactly. The first one is zeta, yeah. H, P, etc. And here it's eta. Yeah. You take the differences, and then you see that what remains is exactly the length of the geodesic, which stays in both whole balls, and that's what I explained at the beginning, that this is the meaning of the Gromov product. And now you define a measure on the boundary, or better to say on the product boundary, minus the diagonal, so psi equal to eta, of course, doesn't make sense. And in the following way. So this is a formula. And this formula, you have now to prove that this measure will be gamma invariant. And this, of course, is a calculation. So if now you want to see how the measure changes under the gamma action on the product, you have to use, first of all, the change of the measure mu p under the action. And you have to see how this Gromov product changes. But it's basically long, maybe not too long, but it takes some time to use properties A and B of the Paterson-Salem measure, the gamma equivariance and the transformation rule, that this quantity actually is gamma invariant, and which will be used to define a measure for the geodesic flow, which somehow descends to a measure on the unit tension bundle of the quotient. Okay, so now, so far we only have a measure on the boundary or the product.
Gerhard, I'm sorry to inform you that your time is actually over. If you could
I'm sorry.
wrap up.
Okay, then yeah, I used a little bit too much time with this explanation. Then next time I will construct this invariant measure for the flow, and then we will, the second step is to compute the entropy of this measure. And it turns out that the entropy of this measure is exactly the topological entropy, so it's a measure of maximal entropy. And then the last point is to show that this measure is uniquely determined by this fact that there is only one measure of maximal entropy. Okay, so that's I will do tomorrow. No, not tomorrow. I think on Thursday. Yeah? On Thursday. Okay. Thank you very much.
Thank you very much. And I can see that Catherine or Lorenzo have a question.
Yes, no, I'm a bit confused. What are the examples besides negative curvature manifolds that satisfy H1?
Which examples satisfy H1?
Oh.
H1 means just the existence of a background metric of negative curvature.
Yes, of course. So besides negative curvature manifolds, what are the examples? What class of manifolds you can study?
So you can study all. So what you do is you take any manifold which carries a metric of negative curvature, and then you can change the metric in the framework of metrics without conjugate points. So you take any metric without conjugate points on this manifold of negative curvature, and you study the geodesic flow of this metric. So in other words, for instance, if you take on a surface of genus at least 2, any metric without conjugate points, it has exactly this condition H1.
Okay, thank you.
Whatever, and then higher dimension depends, because manifolds of negative curvature are not really classified, but you need this background structure to get this hyperbolicity, and the hyperbolicity is somehow used or expressed in this Morse shattering lemma. So Morse shattering lemma somehow uses the fact that you have this background metric of negative curvature. So in other words, what I'm saying here is everything is of course true for surfaces of higher genus. So you can forget all the conditions. The conditions are automatically satisfied for this kind of manifold.
So non-positively curved surfaces.
Is okay. Yeah.
Okay.
Positive
So
curvature and on no focal points and everything is this class of manifolds.
so my question to the proof before, if you have the balls too small, for example, would be in a completely contained in a flat strip, then it would not contain an open set. So you need to be sufficiently large.
Yeah, because if you have just geodesics will stay in a bounded distance for all time, and you can have this, then this projection will, which I explained at the beginning, will only yield 1 point, and of course the measure is 0.
Okay,
so
thank you.
You're not getting anything. So it's a kind of a semi-local property of this measure. So you cannot, in negative curvature, you can make balls are very small, and here you need to have a certain size. That's a difference.
Thank you.
Any other question or remark? If not, let's thank Gerhard again.